This talk is dedicated to differential systems employed in modeling neuronal interactions and convergence analysis for their numerical solutions. The outline of this talk is the following. In the first part, I will introduce a model for the interactions between neurons. Then in the second part, I will present numerical algorithms designed to solve this model numerically. Then in the next part, I will present error bounds for continuous time schemes and also error bounds involving numerical integration. Then I will present results of numerical experiments, and finally, in the last part, I will finish with conclusions and will sketch future plans. This model is expressed in form 1 as a large system of strongly interconnected nonlinear integral differential equations. Here, the most commonly used kernels, represented by bold K, are typically defined as either the exponential function with the parameter tau, or as the quotient involving the sine function at 2 pi t and pi t. This model was introduced by Hoppenstadt and Izhikevich, and they employed the ideas from the monograph by Kuramoto. This system is large, and it includes n equations, where n represents the large number of neurons. Now, because of the extensive number of function evaluations, solving this model becomes time-consuming, and our goal is to solve it in paracomputing environments in order to reduce computational time. If we introduce the numerical scheme 2, each equation is isolated from the other equations in this system. So this means that each equation can be solved by a different processor working completely independently over the entire interval where the solutions are needed. Now, in this scheme 2, the superscript k is an iteration index, and the superscript k denotes the present iterate. On the other hand, the superscript k-1 denotes the previous iterate, and this previous iterate is needed to compute the present iterate. So scheme 2 is an iterative process, and this iterative process can be initiated with arbitrary starting functions denoted by x0 I. Now, together with scheme 2, we will also investigate this more general scheme 3, where x bar represents any solution computed over the interval from 0 to t0. If t0 equals 0, then the first integral is equal to 0. And at the same time, the second integral is from 0 to t. So this means that scheme 3 generates scheme 2. And this also means that 3 is more general than 2, and error bounds derived for 3 can be used to establish error bounds for 2. For the derivation of error bounds, we use the following notation. Here, EKT is the time-dependent vector whose components are the differences between the iterates xikt and the exact solutions xit. So this is a vector of errors at the kth iteration. And now for these vectors, for these errors, we use the double vertical bar notation to represent the maximum norm across all indices I. And we use also such technical notation with di values defined as the integral from 0 to t0, where the integrand involves the exact solutions xi and the approximate solutions x bar I. Here the lowercase d serves as the upper bound for all these di values and also for all errors at t equals t0. So d simply denotes the error as associated with the approximation x bar. Now, this theorem presents an error band derived under the assumption that the kernel is bounded. This assumption is natural because all kernels used in practical applications are bounded. The error band consists of two main components. The first involves D, while the second involves the maximum error of the starting iterate, and this maximum is taken from T0 to T. Both components involve the constant C and the values of T and T0. This theorem implies the following corollary. If we use Q as the upper bound for the constant C multiplied by the function B at T and T0, we can derive this error bound for the maximum of EKT, and this error bound is more concise than the error bound presented in the theorem from the previous slide. But this bound is not as sharp as the one presented in the previous theorem. Here, the function B at T and T0 is defined exactly in the same way as in the previous theorem. So this corollary presents more concise error bound. Now, the subsequent corollary derived from the previous theorem presents the error bound for the case of employing parallel computations over the time interval from 0 to capital T, where the 0 capital T interval is the interval where the solution is needed. Now, in this scenario, the error bound involves the error of the starting function and the value T0 equals 0. Here, the function B at T and 0 is defined in the same way as in the theorem from one of the previous slides. The subsequent theorem presents a sharper error bound than the error bound presented in the previous theorem. This error bound is sharper because it's derived using the specific form of a kernel defined by the exponential function. And this error bound is expressed by inequality 4. And here in this inequality 4, the parameter tau is positive and within the range from 0 to 1 as in practical applications. The functions B and E, both at T and T0, are the same as those in the previous theorem. Now, in this bound, in this error bound, the first component involves the error D, while the second component involves the error of a starting function. Now, this theorem implies the following corollary. Here in this corollary, the kernel bold K is defined as on the previous slide by the exponential function. And if we designate Q tilde as the upper bound for the product of a function B at T and T0 and the parameter tau, we can derive this error bound 5. And this error bound 5 is more concise than error bound 4, although error bound 4 is sharper than 5. Here, the error D is a factor in the first component in 5, while the error of a starting iterate is a factor in the second component. So this corollary presents more concise error bound. Now, the subsequent corollary resulting from theorem 2 is the following. If the kernel bold K is defined as in theorem 2, and additionally, if T0 equals 0, then the error bound is given by inequality 6. Here, the parameter tau is from the interval from 0 to 1, and it's used for the definition of a kernel bold K. The function E at 0 and T represents the error of a starting iterate as before. Now, this theorem presents a sharper error bound than the error bound presented in theorem 1. if the kernel board K is defined by the quotient involving the sine function evaluated at 2 pi t and pi t as inputs, and if t naught equals 0, then the error band is given by inequality 7. And here the function et is the maximum error for the starting iterate over the interval from 0 to t, and the function bt is the product of the maximum of the function a multiplied by 2 epsilon times n minus 1. The next objective is to investigate how the error of numerical integration is propagated in this iteration process. The model is written in terms of integral differential equations, and for the numerical solutions, we solve system 8. Here in this system 8, q, t, I, x, k, and delta t depends on the chosen quadrature. And these integrals appearing on the right-hand side of the model equations are approximated by these values of q, t, I, x, k, delta t. And these values are defined as the sum of two components, the integral involving all iterates xk and the error denoted by the little delta. This little delta depends on the big delta. It also depends on the superscript I, the iteration index k, and time t. And it converges to 0 as the big delta t tends to 0. So system 8 can be written in form 9, and the successive iterates x, I, k, t are solutions of system 9 involving the error denoted by the little delta. So the goal now is to derive an error band for the maximum norm denoted by the double vertical bar and defined as maximum over all indices I from 1 to n. This error band is presented in this theorem. Here in this theorem, we assume that the kernel is bounded by the constant c, and the function little a is bounded by the constant a. Now, the assumption about the boundedness of the kernel and the function little a is natural because in practical applications, they are bounded for all non-negative z. Now, if the function e at t denotes the maximum error over the interval from 0 to t and over all indices from 1 to n, then we get the error band written as inequality 10. Here, the little delta converges to 0 as the big delta tends to 0. The last part of the talk is dedicated to numerical experiments. For the first problem, we use the kernel defined as the quotient involving the sine function. We solve this model over the entire interval from 0 to 10, and the number of equations in this system is n equals 20. After running this numerical algorithm, we get numerical solutions presented in this figure. Here, the red curve presents the solution after the first iteration, and the black curve presents the solution after 2 iterations. Additional iterations give curves which cannot be distinguished from this black curve, simply because they cover the black curve. Now, in problem 2, we use the kernel defined by the exponential function, and as before, we solve the model equations over the interval from 0 to 10. The number of equations is n equals 20. The parameter tau is equal to 0.1, and the parameter epsilon is equal to 0.01. And the numerical solutions of this model for these parameters are illustrated in this figure. Here the red curve presents the solution after the first iteration, and the black curve presents the solution after 2 iterations. And additional iterations result in curves that cannot be distinguished from the black curve. Now, these 2 figures present the mean field activity function for both problems. The left-hand side figure presents the function for problem 2, while the right-hand side figure presents the function for problem 1. There are 2 curves in both figures. The dotted curve, which is obtained after the first iteration, and the solid curve, which is obtained after the second iteration. Additional iterations give curves which cannot be distinguished from the solid curves because they simply cover the solid curves. Now, this table presents the errors which are listed in the last column. The corresponding step sizes are listed in the first column. Numbers of steps are listed in the second column. Numbers of iterations are in the third column, and numbers of kernel evaluations are listed in the fourth column. This table is prepared for problem 2. Now, the next slide presents a similar table prepared for problem 1. And as before, the step sizes are listed in the first column. Then the numbers of steps are listed in the second column. Numbers of iterations are in the third column. Numbers of kernel evaluations are listed in the fourth column. And finally, the corresponding errors are listed in the last column. Now, the next 2 tables present the gain in CPU time. Here, the red NP stands for the numbers of processors. The first table is prepared when the solution is computed over the interval from 0 to 10, while the second table is prepared when the solution is computed over the interval from 0 to 20. In both cases, we used 1, 2, 4, 5, 10, and 20 processors. Okay, so now my time is up and I finish my talk, and thank you for your attention.